Today I want to talk about different ways and different tasks at the intersection of natural language understanding and computer vision. So let me first introduce the tasks we're going to look today at to give you an idea of what we want to do. On the one hand, we want, for example, for a given image, we want to generate a natural sentence description. For example, a little brown and white dog emerges from a yellow collapsible toy tunnel. And this task has been very widely been done in the community, and lots of people worked on this topic starting from last year, roughly. And why is that interesting? Well, I think it's interesting because it can help people who can't see to understand the world around them. And that's not just interesting for images, but just imagine you watch a movie with a blind or visually disabled friend, and he can't really see what is happening. So if we can automatically describe to the blind person that Harry pulls out his wand and stumbles backwards onto the pavement, the blind person has a very good idea what is happening in the movie despite not seeing it. So this is sort of one task we're looking at, telling what we see in videos and images. But then more recently we looked at also other tasks, namely explaining. And what do I mean by explaining decisions we take in visual recognition? For example, if you see this bird, before I started this project, I didn't have any clue what these kinds of birds are, but I could easily describe it with this bird has black and white feathers with white neck and yellow beak. And that's a reasonable description for this image, but it also holds, for example, for this image. But now if we can recognize, for example, that there's a Western grebe, and actually visual recognition systems nowadays are actually quite precise in doing fine-grained recognition and recognizing these kind of birds with like 80 or 90% accuracy. But then this is actually on the right, it's not a Western grebe. So we rather would like to know what is the difference between those two birds, or explain us what does it make to be a Western grebe. For example, the image on the left, this is a Western grebe because this bird has a long white neck, pointy yellow beak, and eye. And of course, the explanation then for the other bird, the Lysan albatross, would be looking very differently. This is a Lysan albatross because this bird has a hooked yellow beak, white neck, and black back. And I think this is important to create understandability what the system is doing, and also create trust to the user, because he can easily verify the explanation, why it will be difficult to verify that this is a Western grebe if you don't have any clue about birds. But everyone can see that this bird has a long white neck, pointy yellow beak, and a red eye. And actually the red eye is like one of the discriminant things for this bird. So that's the second task we're going to look at. The third task is trying to locate natural language expressions. For example, if we have the same image and the sentence here, a little brown and white dog emerges from a yellow collapsible toy tunnel onto the lawn, we found it a bit limiting to just have this description, but we wanted to understand where are those individual phrases located, to be able to understand more better how they relate to the images. So we want to locate all these different phrases, for example, little brown and white dog, and you want to predict where are they located in the image. So the colored box always refers to the corresponding phrase. And this is, I think, useful for many applications where you interact with a smart system and you want to make sure that the system understands what you're doing or what you're pointing at in the real world. For example, if you want to tell a robot what to pick up, what to take, what to do, you have to take your referring expression and localize it or ground it in the world, and especially the visual world. And last but not least, I'll also shortly talk about question answering. And here the task is, given an image and a question, for example, where's the amber cat, to give a natural language prediction or just a single word prediction depending on the data set, and for example answer here on the floor. And interestingly for me, this task requires sort of some tasks we heard previously, namely requiring to ground first the question in the image and then predict the answer from the grounded representation. So as I said, we want to do these different tasks, telling, explaining, locating, and answering, but there's a bit more to it. We want to be that our models not just do this task, but also on the one hand be modular and compositional, so we can allow generalization to other tasks and also train across tasks, ideally. We also want our systems to be explainable on the one hand, as one of the tasks is explain to the user what it is doing, but also ask these researchers to understand our mainly deep neural network models. So what are they actually doing? And for this, it's good if the model are like compositional and understandable. And last but not least, while we have like increasing amounts of supervision, ideally we want to have as little as possible to allow either unsupervised or semi-supervised recognition and description of things. So during this talk, I go through these 4 tasks, and please at any time or even now already ask or interrupt me if you have any questions that I can move faster or slower depending on your interests and questions. So let me start with telling, so captioning. And here I want to focus specifically on capturing novel objects, so on objects which haven't been seen on the training data. But before I go into detail, I first like to describe our general model which we use for image and video description, because this sort of appears throughout this talk. On the one hand, images we typically represent with a convolutional neural network to get a feature vector or feature representation or intermediate embedding. So this is here the CNN in red. And then to generate or encode a sentence, because of the variable length structure of natural language, we typically use a recurrent network, namely a LSTM in our work. So for example, here describe the image, we take in the image feature and then predict a sentence, one word at a time, a dog is jumping, for example. And if we have a video, we follow a very similar approach. We encode the video one step at a time and then predict the sentence. Again, at this example, the same sentence. But we can also similarly encode phrases by encoding them one step at a time. So as most of you have probably seen, this image description was a huge hype last year, and for things which are in the training set, we actually can quite reliably describe images. For example, a female tennis player in action on a court, a group of young men playing a game of soccer. That gets already a bit more difficult if we have movies. For example, here, a movie data set we collected with the reference description as Harry pulls out his wand and stumbles back onto the pavement. A system which we recently proposed just says someone falls on the ground. That's in fact the most important part of this video, but it misses to say anything about wand or pavement. And that's probably because wand just doesn't appear in the training data. There's no movie in the training data, or very few movies in the training data where wand actually appears. So that's what I want to look at in the first part of my talk. How can we describe objects which have not or haven't been frequently enough been in the paired training data but still we want to captioning them. So let's go back to images for now. And for example, if you want to describe this image of an otter, and most systems to do that use Microsoft Cocoa to have paired training data, so have like an image and a sentence description. But otter doesn't appear in Microsoft Cocoa. So what the typical system would say, that's the output from our system, a dog sitting on a boat in the water. That is sort of maybe reasonable, but doesn't say anything of otter, so it's probably useless. That's a bit unfortunate because actually our system and most other systems are actually pre-trained using ImageNet, so this huge database which contains thousands or more categories of images, and ImageNet does contain otter. So they have this information, but they lost it on the way, and this way they can't describe what an otter in a natural sentence. So our idea was to use this unpaired image data, to use paired image sentence data, and also rely on large corpora of text, such as Wikipedia, which talk about otter and other sort of typically all categories which we would be interested in. And the idea of our deep compositional capture is to take all this information and then be able to generate a sentence, an otter that is sitting in the water. And that's actually a generated sentence because you see there's a grammatical error. It should be an otter. So let me summarize what we want to do. We have an image with a novel object which hasn't been seen at training time, and we want to generate a description about this object. How do we model that? So we have a typical caption model where we have here on the left side, we encode the image with a convolutional neural network. And we have on the right side a recurrent network which predicts always the next word given the previous word. And we have a linear classifier which combines the language model and the language feature and the image feature. And this is quite modular because, as you see on the blue, it can be separately pre-trained with a large corpus of sentences. And on the left side, we can pre-train certain classes to learn a classification model for different categories. One important aspect is this multimodal unit here, which allows to actually recognize or describe novel objects. And I'll go into more detail about this now. So this multimodal consists of the language part and the image part. And to actually describe a novel category, let's say in this case it's alpaca, we don't really know how this alpaca looks like in the prediction matrix. So we transfer it from a category which is similar. In this example, we use sheep as most similar and transfer the weights from the sheep category to the alpaca category and switch their activation units for sheep and alpaca. And the transfer is done by using a most similar category, and here we rely on similar ideas which have been done for zero-shot recognition image classification by using a trained similarity metric. In this case, we train a word-to-vec metric to allow us to find the most similar category in our training data. So how do we train that? We have on the one hand Microsoft Cocoa for the paired data, so that we always have pairs of images and sentences. We have unpaired text data using Wikipedia, the Visual Natural Corpus, and UQuac, which is a web corpus. And on the unpaired image data, we just have ImageNet, but we also augmented with words from Cocoa. So for this image, for example, we would also train for pizza, sitting, table, so like all the frequent words which appear in Microsoft Cocoa. And what's interesting, I think, is to look at examples. So in the first example, we transferred weights from plane to spaceship, which we found to be most similar. And if we don't have any transfer, the model would just say a blue and white airplane is flying in the air. But our deep compositional captioner says a spaceship is flying through the air. Or from kite to trapeze, a woman is holding a trapeze in the air. From dress to tutu and from dress to chiffon, a woman is in a chiffon tutu. So that's interesting because actually even two concepts were transferred for a single sentence. For bird to toad, a toad is sitting on the ground.
So in
Yeah?
fourth examples,
yes.
dropping the tennis racket as well. So it's not, is that right? So the whole.
Sorry, in the.
This isn't.
Here.
Yeah, this is more than just concept substitution.
Yeah, because so it's modern concept substitution because our model is also trained on this large language corpus. And the large language corpus knows that chiffon tutu probably is very unlikely to appear with any tennis racket. And they are independently trained models, so they also might just slightly learn different things. But in principle, they have this large language corpus, which hopefully tells them that you shouldn't say certain words with other words. So you get a good language model. Yeah.
Sorry, I missed the part where the transfer is used. So you get word transfers from word to vec.
Yes.
Right? And then you have MS Coco with images and captions for training. And do you basically generate more sentences given similar words? Like, is this done at training time only? Or
No, it's only done at training time.
I see. So you basically augment MS Coco with MS Coco plus some synonyms of some sort, right?
And no, it's more like, if you go back to this model, you have, this is the prediction matrix, which has as output all sort of the output of here are all possible predicted words. So all your, this is sort of all your vocabulary. And you know how to do sheep, and sort of you have the weight vector, which is able to predict sheep. And you want to do now also alpaca in this example. So you take your closest category, which in this case sheep, which we get from word to vec. So we just find the closest category. We don't take any weights from word to vec, just to get a distance measure. And we take all the weights from sheep to go to alpaca. And then we, as I said, we don't want to say sheep for alpaca, and we don't want to mix them up. So we put zeros at the corresponding entries, and we take the sheep for the alpaca. So they're sort of swapped out. Yeah.
So are you under the assumption that you know that this image contains something that you don't have in your training data or not? Because if not, your model should also predict sheep.
No, because the classifier, for example, if the classifier says, which is trained on alpacas, so the visual classifier has to be trained on alpacas. We have training data for alpaca, we just don't have descriptions. So the alpacas will fire here, but the corresponding sheep entry is 0, so it will not say sheep, but it will has a weight here.
That's what I'm saying. The fact that there is a 0 over there assumes that I know there is no sheep in this image, and there's something else that I don't know what it is.
No, it doesn't explicitly said it, because if there would be a sheep, then also the sheep classifier would fire, right? Then it could theoretically say a sheep and an alpaca, because it can produce sheep. Then this will fire, and this will be will have a very high probability. And it can say alpaca, because if the alpaca classifier fires, this will have a very high probability, and then the word alpaca will get a very high probability.
Let me ask one more question. So how did you do your testing setup? Like how do you come up with a set of images that are unknown, that contain unknown objects?
Yeah, so for the most interesting scenario, this is sort of shown here. We have really Microsoft Coco for training the paired data, and we have all like different categories from ImageNet which don't appear in Microsoft Coco.
But for those you don't have any captions?
We don't have any captions, yes. I didn't get yet to the quantitative evaluation, and there we do some appellation where we take out images from Microsoft Cocoa to be able to compare to a reference. But in the actual setting which we want in these examples about, we really have a Microsoft Cocoa as paired data and ImageNet objects where there's no paired training data.
Yeah, so I was going to ask, when you do this transfer and you have alpaca going to sheep or something because it's the closest thing, what happens also if you have like llama going to sheep or goat going to sheep? Because it looks like you're not learning anything different. Is this, if they're all going to the same closest classifier, is this transfer going to not be able to distinguish between them?
Well, it's going to be able to distinguish because it depends on the visual classifier. It will say one word if one classifier appears, and the other word if the other classifier appears. So it depends on which word. Yeah, and then secondary, it also depends on the language model, which also is trained with all those categories. So there's like, it has the classifier on the one hand, and it has the language model to both. Yeah. I mean, there is failure cases. I don't want to say that, but in principle, it can work. Yeah, let's just shortly flip through the quantitative results. So here we have a reduced setting where we actually test on Microsoft Cocoa, but we leave out some categories which we don't see where we don't have paired data. And then we can compute meta, which compares the similarity of the description to the reference. And we compute F1 score, which is if the novel object appeared at all. And we compared to our LSCN at CVPR last year, DCC without transfer and DCC with transfer, and we see in both cases the performance improves. And we can actually capture novel objects, which wasn't the case in any of the other models. So let's maybe go to the second task of explaining why we make certain recognition decisions. And so the example was, again, we have, for example, a bird, and we want to understand why this is a Western grebe. So the input is an image and a predicted class. So you want to generate a description condition that we have predicted a certain class. And how do we, maybe first let me again try to clarify what these different things are. So an image description is just about an image, while a class definition which defines the class is just class discriminate, but it's not relevant to the image. It might just be general, but not actually talking about a specific image. And a visual explanation is hopefully both, namely matching the image, but also being discriminative to the class. For example, the description of this bird is, this is a large bird with a white neck and a black back in the water, while a class definition is, this Western grebe is a water bird with a yellow pointy beak, white neck and belly, and black back. While this explanation is then, this Western grebe, this is a Western grebe because this bird has a long white neck, pointy yellow beak, and red eye. So it can be, especially for those birds, that a class definition and explanations are quite different, quite similar. But for example, here, if we have two lice and albatrosses, the definition will be always the same, but the explanation will focus on things which are visual. For example, here it will say it has a large wingspan because you really can see this bird has a wide wingspan. So let me walk you through our model, how we do this. So we have just a fine-grained classifier which recognizes the bird class. For example, in this case, the cardinal, and also gives us a deep embedded feature about this image. And then we have a recurrent network which predicts the sentence. And this is this part of the model. This is a normal sentence prediction framework in which just predict the sentence, and it will also be trained like a normal image captioning model. However, we have the problem that it's actually difficult to collect explanations because you actually need an expert to tell you what is discriminative. And what we did instead, we took normal descriptions but trained them in a way that they become explanations. And to do that, we introduced the discriminative loss in addition to the normal relevance loss. And the discriminative loss takes the description which is produced by the model and tries to predict from it the class. And if we can predict from description the class, then obviously we are discriminative, because if the description is telling enough what we can that we can get the class, obviously we have a discriminative sentence. And we do that using the reinforcement trick, because we want to we sample from our model, and then we want to judge if the sentence is correct or is discriminative or not. So we have a reward function here which goes over this sampled sentence.
So is that part, is the reward function trained, or you're actually fixing it?
So the reward function is at training time. So this is only about training time. At test time, there will be no reward function. There's a sentence classifier which is jointly trained to predict from the sentence the class. And if we match the class, it gets a positive reward, and otherwise a negative reward.
Basically, you have the classification loss.
Yes. Yeah. For the sentence, yes.
What's the reward of this classification?
Yeah, so it only works if you really sample from the entire model, because so the normal relevance loss, we know what to say per word. So we have a reference for each word. But in this case, we want to judge the loss for the entire sentence. So we want to get a gradient for the entire sentence. So we need to look how can we judge this entire sentence and what would be the reference. And we don't really have a reference in our training data, so we have to sample from our model and then see, is this a good one or not? And if it's a good one, we can, this is like our new reference, that's sort of the reinforcement rule. And then we can populate the gradients for each word if they are correct or not.
And then what is the difference between the loss and then the percentage we lost there?
So here we can compute a loss per word. So, so the typical model, which I had at the beginning, is you predict the first word and you compare it to the reference, and then you take the next word and compare it to the reference, and so on. So you can really compare each word. But in this case, we don't have a reference sentence. So we have to sample from our model and take this as a new reference.
But there isn't your reference just the category which is cardinal? Because you're saying, given a sentence generated by the LSTM, you want to predict that the category is cardinal.
Yes.
So your ground truth is just cardinal. It's just a category.
Yes, but if you would just put this as a loss, we wouldn't know which of what would be the loss for all of the words, because it doesn't give you a loss like a gradient for all individual words.
I see.
How does this give you visual words? Like, couldn't it discover words that are non-visual? Like, I don't know if the definition says flightless bird.
Okay, yeah. So we Yes, it could introduce also non-visual things, yes, that's true.
Did you see that happening?
So that depends a bit on the data. So our descriptions are mainly visual. So the descriptions which were collected for this data set asked users to describe what they see in the image. So typically, you wouldn't get anything which is not visual. And basically, we train on those descriptions, so we can deviate from them, but we can't introduce new things which haven't been in descriptions. We can sort of focus them to be more discriminate, but we can't suddenly say that's a flightless bird because this will never appear in the training data. Yeah.
On the discriminative loss, if I were to look at the system, the LSTM part looks like a sentence sequence decoder, right? Takes a vector and
Yes.
a sequence of things.
Yes.
And I would think that, well, for the discriminative, it took an encoder to take a sequence of things and pack them back into a word. Why is that different than the discriminative loss that we're using? Or is it different, or is anyone better? If you tried that?
So you mean you can start encoding this?
Yes, into
Yeah.
a vector. Roll them back all the way back into the vector and do just the standard sequence vector.
Yeah. So the sentence classifier basically does that. It's an LSTM which reads in the sentence one word at a time,
Okay.
and gets the reward if it's correct or not. Or it gets sort of, you could theoretically backprop the loss, but it wouldn't capture sort of the diversity of the model, because you would always just get sort of your maximum score. But maybe it's a thing which we didn't try here.
Just so I understand, so the relevance loss is, that's the generated word given the previous word
Yes.
that you've generated.
Yes, that's correct.
And not the reference, not the target sentence, then it's just cross-linking with the target sentence.
Yes, yeah, for each single word. Let's look at some qualitative examples here. So the first one is a definition, and this one we trained as a normal description model, but we trained across all classes rather than across the class rather than for a specific image. And we see that, for example, in this case, it's not image relevant because it's not really blue. We have our normal description, which says this bird is nearly all black with a short pointy bill. We have, just using the label and not the discriminative loss, we get this bird is nearly all black with bright orange eyes, which is sort of correct. And if we only have the discriminative loss, we get this black bird with a red eye and a white beak. And the most precise explanation we get if we use both the discriminative loss and the label as input with this black bird with a red eye and a pointy black beak. We also evaluated this quantitatively. On the one hand, we have image relevance by using the normal Meteor and Cider scores, and we see that our explanations score slightly better than the ablations. And we also asked bird experts who know about birds, and asked them and gave them all these 5 different versions, and asked them what is the best declination with respect to correctness, and also with regard to discriminating those different entries. And they had to rank it on a scale from 1 to 5, so they always had to make a ranking. And we see that our explanations have slightly wins over all the other approaches. Yeah.
So this domain has some unique attributes, obviously, in terms of explainability. I wonder if you think if you take a much harder domain, let's say, explaining why Netflix recommends a movie, which they actually also want to do for the same reasons you said, but their explanations are kind of approximate. They give you it's because you like this other movie, but that's not really what's going on. I guess my question is, to what extent do you think these techniques that you've outlined would map over to this domain that I think is much more difficult?
It depends a bit on the exact setting, but I think that the core, I think there's two core ideas here. On the one hand, not looking only at the description, sort of what we have in our training data, but move away. So we sort of have this loss which allows you to move to another direction. And if you have some way to formulate that, you can use reinforcement learning to go in this direction. And this direction can be any direction as long as you can give it some reward. If you have this model is more flexible than the standard backpropagation because we just need to give a reward to it. We don't have to have a gradient for all words, for example, because we sample from the model and then use that.
Right, so it's appropriate. I guess one if you considered, for example, injecting noise, right? So I'm basically saying, right, the direction here seems very clear, right, for the gradient. If you inject noise into this can be a simulation of what might happen in another more difficult domain. And so I guess one way to pose the question is in terms of how robust is your method to noise?
So yeah, so we haven't explicitly tested for that. Definitely, sort of these descriptions are all collected on Amazon Mechanical Turk, and there's naturally a noise, so not all the descriptions are correct. And that's actually something we find generally for descriptions. The average description we got from Amazon Mechanical Turk is actually more noisy than a good description generated by our system because it learns to produce a more robust sentence description. We haven't explicitly tested it for like this explanation models, but for lots of our description models, they are typically grammatically better than the average description because the model learns to filter out this noise. Yeah, so we didn't test anything beyond that. Any other questions? So let me summarize visual explanations. So explanations are relevant to the image and discriminative class, and they allow to teach us and learn about categories. They also allow, hopefully, the user to trust the system because they're more easily to verify than a class position. And our model, as I already just mentioned, sort of allows to change, for example, description to an additional objective. That could be here, as we showed here, for explanations, but also it could be encouraging to say or ignore certain phrases, or it could optimize for blue or meteor, sentence length, or other things. So we have two more left, and I'll go over them a bit more quickly because we are running short of time. So we also wanted to look at locating or grounding natural language phrases. And so this means we have given a sentence, for example, little brown and white dog emerges from a yellow collapsible toy tunnel on the lawn. We want to find all these boxes there. And let me shortly highlight the idea. We encode the phrase, again, with a recurrent network. And we have lots of bounding box proposals. And we want to attend to the right box which presents this phrase. And we want to do that with a minimum amount of supervision. So what we do, we try to attend to the right bounding box, and then we try to reconstruct again from this bounding box the input phrase. And this allows us to learn this problem without any additional supervision. So we have a reconstruction loss. We can encode the phrase and reconstruct the phrase. And let me just show some qualitative examples for this task here on the Flickr 30K entities data set. For example, a man walking by a sitting man on the street, we get them all correct. A white dog is following a black dog along the beach. Here the beach is not fully correct, and there's also more examples. We can also train them with not just the reconstruction loss, but we can also, if we have grounding, for example, for some of the phrases, but not all. We can have an additional attention loss, so we can have like a semi-supervised setting. We can have for some, we can just use the reconstruction loss, and for others, we can also have the supervised setting, and that allows sort of both ways of training. And as we can see here, we get around, we have like 2 different features, but in general, we get around 24 or 32% accuracy, and if we increase the amount of annotations, we can significantly improve the performance. But it's like flexible to go from 0 to 100.
The networks in the previous image, are they pre-trained on other datasets?
No, in this case, there's nothing pre-trained apart from the image recognition network, which is pre-trained on ImageNet. So the image, I think in all our experiments, the image network is always pre-trained on ImageNet. Let me skip over that. Just one word maybe to say we can do something very similar for segmentation. So instead of using the bounding box, we can also predict the segmentations. For example, 3 people on the right, we can segment that, or anyone, or a big black suitcase, we can segment the area where there's black suitcases. So maybe like the last 2 minutes on visual question answering. And the main idea here is this task is to understand the question and predict the answer. And the main idea is that we want to be modular here. And we take the image, take a CNN, and predict basically features all over the image. But then to answer the question, we have the amber cat. We sort of need to know, we need to have a module which predicts where is amber, and we need to have a module which predicts where is cat. And if we know where amber is and where cat is, we can combine these 2 predictions and have a where module, and then hopefully predict floor. And the main idea is here that these modules are trained across all questions. So for example, if the question would be, which color is the cat, we would use the same cat module. So we have modules which have names, and they are composed, so that this entire network is composed on the fly depending on the question to predict the answer. And these modules have to eventually learn we don't say what they have to learn, but given all the different question and answer pairs, they eventually figure out what cat means, what amber means, what is to predict where, and what it is to predict color.
Is the structure of that network based on the parser, or does it learn the structure?
Yeah, so that's a good question. What is missing here is, what I didn't say it, is how can we get this network structure? And we take sort of the most simple approaches. We take a standard natural language parser. In this case, we take the Stanford parser, and this gives us sort of a network layout which you just sort of prune and get this simple parse tree. There's the option which we also looked at. If we have multiple parse trees, how can we select among of them? And we use a very similar idea as I described for the explanation. We use reinforcement learning to predict which of the parsers is the best one. And we see here on the visual question answering data set that we can perform competitive with our neural memory networks, which perform better than an attentional approach only, or just having a full frame vision. And I think I should conclude at that point. With saying that I showed you this 4 different tasks, and on the one hand, they are modular. For example, when we capture novel objects, we try to be modular. And the neural memory networks are also modular because they have these different components. But we also are able to explain our networks to the user, but we want to also understand what our networks are doing. And for this one, we looked at grounding natural language, but also our neural networks. If you remember, they are these individual blocks, so we can understand what each of the components is doing. And for supervision, I shortly talked about that we have variable levels for grounding, and for the captioning of novel objects, we didn't actually need training data for all of those different aspects. What do we have as future work? On the one hand, for modularity, I would like to look at learning multiple tasks jointly. So description, grounding, and VQA, they seem very similar, and ideally lots of our modules would allow them to be trained jointly, and we just sort of didn't get to it yet to make this all work together. I told you that we want to explain to the user what the network is thinking, but what we didn't get to yet is how to explain internal network decisions. That would allow us researchers even more to understand what is happening to the network if we would not just generate an explanation, but also be insightful why they made this decision, or what was most important to make this decision. And we did explanations, but we didn't ground them so far, so that's sort of the other thing we want to look at. And with respect to supervision, we like to scale to really large scale. If we have semi-supervised learning in place, we can scale to much larger data sets because we don't need all the supervised training data sets we have been using so far. And with this, I'd like to thank you for your attention and all my collaborators who worked together with me on the different projects here. And I'm happy to take any questions.